Well, good morning, folks, and a very special welcome this morning to our colleagues from the Inamori Foundation. This is Inamori Kanazawa herself and the team from the Inamori Foundation, to Oxford colleagues from across the university. Delighted to have those of you for whom this is your first time in the Blavatnik School. And a special welcome to students from two local schools, from Cherwell and from St Edward's School. You're very welcome in the Blavatnik School of Government, and come more often, is what I would say to you. This morning, we have the delight of hearing from Sir John Pendry, for whom I just want to say congratulations once again for the 2024 Kyoto Laureate Prize in Advanced Technologies. It's a wonderful achievement, and we're all going to find out exactly why he won it in a moment. I just wanted to say a welcome as well to Professor Andrew Boothroyd, Oxford colleague, Professor of Physics, who will lead and moderate the Q&A after Sir John Pendry's address this morning. Nobody could introduce him better than he himself in his own words, so let me step aside and share with you a word of introduction about Sir John Pendry.
First, I didn't know that these things I was interested in was called science, and eventually learned that. So I used to go down there and do chemical experiments, some of which were quite dangerous. I was a very dangerous little child. There are two processes in creation of an idea, I think. One is to get an idea of what the important problem is, and that comes about through discussion with your colleagues. You have to know what they're working on. You have to be aware of what's possible experimentally. So you not merely got to ask them what they're working on, but how they do it. But that second process doesn't involve a lot of people excitedly discussing in a room. That sets the problem. You solve problems by hard thinking on a rainy Sunday English morning. Metamaterials actually look and behave like ordinary materials like glass or metal or so on, but they have very unusual properties. They give access to a very, very wide range of properties.
Good morning. Thank you for your kind introduction. I have forgotten one thing, and that's my one experiment I'm going to do. So I will extract that from my bag. So I'm going to talk to you about light. And you all know what light is, so that's a good start. It's been with us for as long as man has existed, and before that. And in fact, it's so central to our lives and our understanding of the world that when in English you say, I see, it means I understand. So light is how we primarily speak to the world. And so people have been interested in it for many years. So you might think, as I thought, that everything that there is to be known about light, and particularly after the brilliant work of James Clerk Maxwell in the 19th century, that there was nothing further to be known, certainly not about classical light, which is what I'm going to speak about today. But that turned out not to be true. There are many more things, deep things, still residing within light and electromagnetism that are there to be found. Now, obviously, if you want to work with light, you've got to control it. And if you're going to build devices, you need to make them out of something. You need to make them out of a material. And it so happens that the materials available to in optics and other regions of the spectrum, such as radar, they're rather limited. And you really like to have materials which have properties which you cannot find in nature. Now, I do hope this clicker will work. It did earlier. Yes, good. Okay, right. So my talk's going to be in 3 parts. I'm going to tell you what metamaterials are, and then I'm going to go on to show you some of the things that other people have done with them that have actually made them quite useful in the world. And then, very, very briefly, because from past experience, I know I'll be almost out of time at the end of those 2 sections. I'm going to have a brief slide telling about what the future might hold for metamaterials. What are they? Well, you all know that conventional materials owe their properties to atoms. And it's the way the atoms respond to light that dictates how a material evolves. But you don't see the individual atoms. What you see is an average over it. And because you see that average, you can describe the material in terms of collective properties like the refractive index, for example. And to be able to do that, to be able to use a refractive index, there has to be a big gap in size between the size of the atom and the wavelength of light, because within that wavelength you have to average over many millions of atoms. And that factor in ordinary materials is a factor of 1,000. And it turns out it doesn't have to be a factor of 1,000. It could be as little as 10. So there's lots of room in that gap between the wavelength and the size of the individual thing that's responding to have something that's a lot bigger than an atom, something you can actually make. And that's the property that a metamaterial has. Its internal ingredients, its little manufactured atoms, if you like, are small, but they're a lot bigger than an atom, and they're a lot smaller than a wavelength. But because you can play with that structure, using the structure, you can alter the properties of a material without having resort to chemistry. We use chemistry as well, but we've been doing that for a long time, and we've pretty well exhausted its possibilities. And that's why we turn to metamaterials. I'll give you a simple example in things that you know about already. So if you look at a metal, such as silver, you usually think of silver as something that's highly reflecting, a mirror, silver mirror. But you also know another form of silver. If you've seen these old black and white negatives, the black in it is pure silver. And the difference between the mirror and the negative is that in the negative, the silver has a different structure. It is very, very tiny nanospheres, about 50 nanometers across. And that change of structure, without changing the chemistry, changes something which is one of the best reflectors we know to one which is one of the best absorbers we know. The silver blacks and the gold blacks are actually used in thermometry to absorb light. Now, if you look what that atom does when it responds to light, essentially an atom consists of electrons bound to protons, and when an electric field is applied, it pulls those entities apart, and the response is dictated by a transition between the orbitals of the atom. And the typical response looks like this. Oops, yes. So depending on how fast you try to polarize the atom, so at very, very low frequencies, the electrons polarize in the same way that you're pushing them, in the same direction you're pushing them. But there comes a frequency called the resonant frequency, in which this transition goes from positive to negative. And that may seem a bit strange, but you can do a very simple experiment in which this happens. I don't have a piece of string, but never mind. I'll imagine a piece of string, just of our other prize winner, Bill Forsyth, did yesterday. So imagine this is a pendulum, and then I'm going to move the support like this. And if I move it slowly, the bob on the pendulum will move how I push it. But I'm going to move it a bit quicker. And then when I move it faster than the resonant frequency of the pendulum, it will go like this. It will go in the opposite direction to which you push it. And that's exactly what happens in an atom. They're both resonators, and all resonators behave in this same strange way that they reverse the way they respond if you try to push them too quickly. So that's the basic unit, and when you put them together, you can do useful things with them collectively by refracting light. Now, this is the prototype metamaterial we constructed in the mid to late 90s. And the idea here was to create magnetism without magnets. So these are some rings made of copper. And if these rings were complete, then if you put a magnetic field through these rings, a magnetic field induces a current which flows around the ring, and a current flowing around in a ring, in turn, creates a magnetic field. So by making a loop of metal, you can get a magnetic response from a material like copper, which is not magnetic. But this particular structure does something in addition. It doesn't allow the electrons to flow right around the ring. It's a split ring, which stops the electrons from flowing around. They do flow around, but the way they do this is they jump this gap here. Okay, so they go round, across, round, and across back to where they came from. But in jumping that gap, it's not like an ordinary conductor, it's a capacitor. So a space between two metals makes a capacitor. And if you're an undergraduate in physics, you know the response of a capacitor. You'll also know the response of a system which makes electrons go around in a circle. It's an inductance. And so this is another example of a resonator. If you put a capacitor and an inductor together, it makes a resonance with a certain resonant frequency. And it has all these properties which I showed you before for the atom. Why is that bothering me? Dismiss. Okay. All these responses which you see for an atom. So you can see that this little resonator, which you can easily make you don't even have to make them yourself. You can write off to companies which make printed circuit boards, and they can make one of these for you. So out of those, we can fake an atom, if you like. And here's a paper which I gave at Laguna Beach conference in 1999, I think. Yes, 1999, here. In which, together with my colleagues at GC Marconi, we published these ideas about faking atoms with these little resonators, which you then stack together in a big array. And that, to our surprise and encouragement, created a lot of interest. And in particular, David Smith at UCSD at that time got very interested, and I'll talk about David's work shortly. So since that year, quite a lot of groups got interested in metamaterials. So there were two key events. So here's the 1990 1979 paper. And actually, we didn't call them metamaterials at this point. And the metamaterials name was only coined somewhat later. But this was the start of the use of these split ring structures to do some strange things. One that I will talk about quite a lot is negative refraction, and that was published in 2000. And you can see there's a bit of an induction point, and then it begins to take off. And then we talked about the cloak, which gave another positive kick to it. And so it goes on to 3,000 or 4,000 publications per year at the current time. And one very rewarding part of this increased interest is it's actually come by the field diversifying way beyond electrical engineering and physics. It goes into acoustics and all sorts of other areas too, some of which I'll talk about briefly later on. And this is just to show the width of what we're talking about here, applied physics, if you like, electrical engineering, optics, of course, nanoscience, physics, telecoms, so on and so forth. You can read the slides for yourself, I'm sure. Now, this was the first realization of the split ring structure. It was made at the Marconi company, and it, as I explained before, it was not manufactured by Marconi. It was designed on a computer. The computer file was sent off to a company that made printed circuit boards. They etched the copper on the board, and this is what came back, which is the split rings I talked about before. The dimension's about 1 centimeter across. The resonant frequency is 10 gigahertz, because those are the radar frequencies that Marconi were interested in and why they asked me to invent this structure. And the ease of manufacture was one of the reasons that it did take off. So these structures did extraordinary things from the point of view of electromagnetism, but they were extremely easy to make. You didn't even have to make them yourself, you designed them. That's one reason why it took off. And then, of course, they're not confined to radar waves. They can work in the near-infrared, the telecoms wavelength. This is a structure designed. It was called the fishnet structure. Again, it's a resonance, and you can see the structure here. It consists of alternate layers of silver and a dielectric. And that's a resonance structure designed to give negative refraction. Here's an electron micrograph of the actual structure itself, and at the side with the layers resolved. And the length scale is 1 micron. A bit more expensive to make than the split ring structures. Now, I did mention negative refraction, which is one of the properties which you can engineer with metamaterials and only with metamaterials. And negative refraction was first discussed by a guy called Victor. Sorry, I seem to have gone. No, that's fine. Negative refraction was first discussed by a guy called Victor Veselago, and he published his papers, at least in English, in 1968, a very long time ago. And he said if you want to have this property of a negative refractive index, which nobody had ever heard of before, he said you have to do 2 things. One was to make the electrical response negative, and the second thing was to make the magnetic response negative. And for those of you who like formulae, you can see that if you take the square root of minus times minus, you might expect to get a minus sign. Indeed, you do. There are more sophisticated arguments for the negative sign, but that will do for now. Victor caused quite a stir with his announcement of this possibility, and he had a great time touring America, giving lectures and getting fees for it. But the whole thing fizzled out because nobody could find anything in nature with a negative refractive index. And I think that's a lesson to theorists like myself. If you invent something or think of something that people can't do and make, then it's going to gather dust on a shelf, and people will rapidly forget about it, which they did, because I certainly had never heard about it before we started making these metamaterials. So why is that so interesting? I mean, we all know about negative numbers. Some of us know about imaginary numbers. What's the big deal about a negative number? Well, if you know about Snell's law, which says that if you have, let me get this thing going. It's not as clever as it looks, is it? I want to point over here. Okay. I paid 150 quid for this device. Anyway, let's go back and start again, shall we? Okay, good. Right, so positive refraction means that if the light comes in here, it emerges on this side of the normal. That's defined as positive refraction. That's what glass does, that's what water does, that's what everything does that we knew about before this stuff. But if you have a negative refractive index, it goes this way, the wrong side of the normal, to satisfy Snell's law. Those of you who know Snell's law. And it is a big deal because this implies something that is really rather strange. Now, I should mention that there are two velocities to light, and they're usually the same. One is the velocity that you see if you make a packet of light like this. So you make a little pulse or packet of light like this, and then you watch how the shape of that packet moves. And that's called the group velocity. And that's where the energy goes, because all the stuff inside this packet eventually ends up somewhere else to the right. To your right? Yes, it is. But there's another velocity, and that's the velocity which the waves inside that packet take. And they can be different, and they are different, very different in negative refraction. So these waves actually are traveling the other way. And they have to do that. You can't avoid that in negative refraction because if you have a ray coming here, then this is a law of mathematics, not of physics. It says that the projection onto the surface of this guy here has to be in the ratio of the refractive index. So if this has a positive refraction here, then this has to have a negative projection on here. So it goes in and out, and it makes a chevron shape. Now, the waves can't do that because there is another law which says that the parallel component of the wave vector, rather than this velocity vector, the parallel component of the wave vector has to be the same inside and out. You can't break that law. And this means that given that the wave velocity is parallel to the ray velocity by symmetry, it has to point this way. And so you're stuck with this thing with negative refraction, that the two things are going in opposite direction, and that is the first weird thing. And it hits you right in the face without any mathematics, just laws of symmetry. So we knew that this was weird. So can you make something that is weird? And the answer is yes, because at that meeting at Laguna Beach was David Smith and Shelley Schultz, two people who became my great friends. Shelley, sadly, is no longer with us, but David is now at Duke University, and we continue our collaboration over the years. Now, David took hold of this concept of the split ring, and I've already said that a resonator can turn negative if the frequency is not right. So here's the split ring resonator again for you. And at the operating frequency, it has this negative response. The magnetism goes in the opposite direction to the applied field. And also, you can't see it very well, but can you see that little shadow there? That's on the other side of this board, and it's a wire, just like an aerial. And that is another resonator, but now it resonates the electric field, not the magnetic field. So you've got two resonator things doing their resonant thing, And because you have this flexibility of structure, you can never get the two together in nature, but you can actually engineer it so that the two negatives occur at the same frequency. So this is the first structure made with a negative refractive index. They didn't know that at the time, and nor did I. But it went to the referee, and the referee said, hey, here's something way back that tried to do the same thing and failed. And that's how we learned about Victor Veselago. And it was a marvelous thing for Victor, because the experimental realization of what he talked about all those years ago meant that he was now famous. And he came on the tour again, and he was now 80 years old, and he had a great time, I can tell you. He's a great Russian bear of a man, and with a lovely nature as well. Not all Russians resemble Putin, I'm glad to say. Okay, so that was one thing that happened. Now, there's something else. If you can do extraordinary things with these metamaterials, and they can produce properties, not quite to order, but they can do many things, then you want a design tool. And I'll just peek ahead to see what's coming next. But okay, you want a design tool, and this design tool is called transformation optics. Now, the problem we have is that the old optics works in terms of the ray approximation. It is an approximation. It describes the way things refract at a surface, negative, positive refractive index. What it doesn't have an inkling of is the wave nature of light. So it doesn't tell you that light can also, as well as refracting, it can divide into two and reflect from a surface as well. It doesn't tell you about that. And what does is a description in terms of the electric and magnetic fields. Now, I want to talk a little bit about fields, because this, at the beginning of the 19th century, people still thought in the terms of Descartes and Newton and other people who the forces they knew about, they described in terms of action at a distance. So two gravitational bodies, for example, the Earth, the Sun, they attract one another, and the force they create between one another acts along the line separating them. And it's action at a distance. So if you took the Earth, if you took the Sun away, the Earth wouldn't know anything about things. And if you took the Earth away, then there'd be no force. But Faraday, who was a genius, but he was mathematically illiterate. He had correspondences with Maxwell, who definitely wasn't, saying, "Can you not describe your mathematics in terms of words, sir?" And it turns out Faraday could. And his choice of words was this concept of a field. And some of you will have done this experiment. You take a bar magnet, put a piece of paper on it, and you scatter iron filings of it. Who's seen the iron filings experiment? Any of the sixth formers? Has your physics master done it? I see some nods. That's great. And Faraday did that. It wasn't the first. But what he saw were lines of force. You know this thing that looks like a spider? Yeah? That was Faraday's mathematics in words. They were his fields, okay? And he made a postulate. Now, in philosophy, it is usual to use something called Occam's razor. And Occam's razor says, if there are two ways of describing a phenomenon, you pick the simplest. Faraday didn't. He introduced this complication of a field. So you have this intermediary. First, the magnet creates the field, and that is a reality independent on whether it's acting on another magnet. And then it is the field which interacts with a second magnet. So this concept of a field was born, and there are magnetic fields, as with the filings, but there are also electrical fields as well, a very similar nature, and there are all sorts of properties. Now, field theory, based on this idea of objects being surrounded by a force field, independent of what they're acting on, enabled physics to go forward. And indeed, it's the basis of the very most modern ideas in quantum mechanics. They're all based on field theories, invented by a mathematically illiterate Faraday. There you go. Words matter after all. So, there are the fields. Now, they in fact were used by Maxwell to give his very complete description of classical electromagnetism. So everything in classical electromagnetism is contained in Maxwell's equations, and the basis of Maxwell's equations are these fields. And because you can draw lines of force, they're very like the rays of light, except the description is exact. So we're going to work in terms of the fields, and I can draw pictures of the lines of force where these fields go, just as Faraday and Maxwell did. Now, somebody else who was interested in fields was Albert Einstein. And he was confronted with a problem, or confronted the world with his problem, if you like, in general relativity. As I've explained, Newton and others thought about gravity as action at a distance along the line separating the planet and, and the sun. But Einstein said, no, that can give a wrong description of things. And he said that the way to describe the motion of a planet is in terms of a force field which surrounds the sun. And to do this, Einstein thought of space in a different way. In the 19th century, people struggled to find a name for emptiness of space, a vacuum, a void, emptiness, nothing. But Einstein said, no, space is just another material. It has a refractive index. He called it the metric, but we'll call it refractive index. And what's more, you can change it. So not only is space a material, it's a deformable material which you can squash and stretch and so on and so forth. It's made of rubber, in fact. And one of the things which can squash space is a gravitating object. So the sun, for example, squashes the space around it, and that makes the space, gives it a higher refractive index than there's an otherwise unaffected vacuum. And this enabled one of the key predictions of general relativity, which was that in Newton's notion, because it was only gravitational objects that are massive objects that affected one another, and light is massless, right? The photon has no mass. Then light is unaffected by gravity in a Newtonian picture. But Einstein said, well, light moves through space, and if you change space, especially if you change its refractive index, light's going to be bent. And Arthur Stanley Eddington in 1919 made this great experiment when he observed a solar eclipse, which is the only time you can see a star pass behind the sun. And as he observed the passage of the star, its apparent position of the sky, as observed by a telescope, was bent to another by an incredibly small amount. It was a very difficult experiment, and that was one of the cornerstones of the experimental proof of Einstein's general theory of relativity. And in fact, now we have even more dramatic evidence of that. This is a picture of a very, very massive red galaxy here in the foreground. And behind it is a blue galaxy, which you could not see because its light could not go through the red galaxy, except that the red galaxy is so massive that it's made a lens, and it's made a sort of cloak in that the light now goes around the galaxy instead of trying to pass through it, and that ring is an occasion of gravitational lensing. So thank you very much, Einstein. We're going to borrow some of your equations. Here are Einstein's equations. What they tell is that if you bend space, and this is the way Einstein describes the bending of space with his metric, the derivative of the metric, and this tells you how it changes epsilon mu for space, and hence the refractive index of space. So you don't need to know about that, except that it's there to calculate if you need to. And we do need to, because the way transformation optics works is that Andrew Ward and myself some years ago realized that if you deform space which already contains electric and magnetic fields, then what we realized is that these fields act as though they were embedded in the rubber sheet. So you stretch the sheet, and inevitably you take these lines of force with you. So the way we control light is to have this imaginary rubber sheet. I sometimes think it's real, but it's imaginary, of course. And you stretch it, and as you stretch it, you pull these lines of force to be where you wish them to be. And then you describe this distortion. You think of it in mathematical terms as a coordinate transformation. So here's a Cartesian coordinates, and here's a complete mess of coordinates that you created by the stretching described by this transformation here, Mr. Einstein, and I get my epsilon mu. Quite straightforward, I hope. So that's the theory, and we were quite excited about that. I hope you were terribly excited by those equations, yeah. But we realized that perhaps not everybody was blown away by differential equations. So we thought, what can we do? And the idea was that we make something invisible. And I didn't know about Harry Potter in those days. That was my wife's reading hobby. So she told me about platform down in 3/4, whatever. What I knew about was Peter Pan. Now, if you want to make something invisible, it's not enough to make them black. That's conventional stealth technology. You take a big pot of black radar paint and you splosh it all over your ship or whatever, and it won't reflect radar waves. Fine, it works well. I designed some myself. But it's not enough, because you're left with a shadow. And why do I show you Peter Pan, his statue in Kensington Gardens, just north of my college? I show it to you because he's a little boy who lost his shadow. And when he loses his shadow, you really can't see him, and he is invisible. So how to do that? The prescription is very simple. So what we want to do is, first of all, we define this medium here in which we want to hide something. So the rule is that no light can pass through that object. So you've got to steer every beam, ray of light that comes through this object, steer it away from that. And the cloak has to do that. And the cloak is contained in a finite region of space, because you don't want your cloak to be infinitely big. It has to be finite. It isn't a Harry Potter thing. Sadly, it's more a Harry Potter shed than a cloak, I have to say. And the other thing you have to do, because of the shadow thing, is that when you're done steering the rays around this object, they have to emerge in exactly the same trajectory that they were following before they hit the cloak. It's a nightmare PhD project. Okay, kid, go away. That's the problem. Come back in 6 months, solve it. How would you solve it? Of course, it's not just for this one set of rays. They can come in here, there, every possible angle, and the cloak has to work for every single one of them. Okay? Might take a long time, yeah? Even with a computer. So how do we do it? Well, rubber sheets to the rescue. So I'm going to imagine that this whole area, which contains the cloak and the object I'm going to hide, is contained within, let's say, a sphere. It doesn't have to be let's say. And I'm going to poke my finger in the middle of that structure, and I'm going to make a hole in space. And all the rubber that was filling the whole sphere, I'm going to push out into an annulus like that. I'm going to squash space, so I'm going to make it more refracting. And then there are many ways you can pack that stuff into this annulus, but the simplest one is just a linear compression like this. If you like transformations, this is the transformation I use to squash space into this region here. Sorry about the extra formula, but you can see what I'm doing. I'm just squashing stuff up. And then I turn to Einstein and I say, please tell me what metamaterial I must make to have all this stuff carry the light in the way I want it to. And yeah. Now, how does that achieve what we do? Well, remember these little laws about the rubber sheet. So if you distort the sheet, it takes the light with it. It takes the fields with it. So by making this hole and pushing and compressing, we've actually pushed all the fields into this region here. It happens automatically because they have no choice. They're stuck to the rubber sheet. But I have only deformed the sheet within this cloaking region. I haven't touched the rubber outside. Therefore, the rays do not move. So in one stroke, one simple formula, I've written my PhD thesis. And indeed, a cloak has been built. David had then moved to Duke University in North Carolina. He built it for radar frequencies. It's a cylindrical cloak. It has these metamaterial structures which you can see, and they grade their properties in the way that Einstein told us, from the outer edge to the inner edge. Here's a picture of how they go. And that experiments were done on that, and it verified that it worked after many computer simulations and so on and so forth. Right, now, the other thing I want to show you can do with transformation optics, or explain, is how this Veselago lens works, because what is the Veselago lens? Well, Veselago realized that you could actually make a lens out of this. I'm going to get this thing sorted again. Okay, so if you have negative refraction, you make this chevron shape at the surface. You can see just in a ray picture that you'll get a focus inside if the material is thick enough. And then, actually, you get a second focus outside. So it's the Veselago lens. It's a strange thing. The image is exactly the same size as the object, so maybe it's not quite so useful as a lens. But it does have a strange property. It doesn't have many of the aberrations you expect with a lens if you design it right. And I thought, there's something there. Scratch the surface, you know. Kelvin once said in 1900 that physics was done, and there was only two small problems no bigger than a man's hand on the horizon. One turned out to be quantum mechanics, and the other turned out to be general relativity. So, you know, small things. And the small thing I spotted was this strange perfection of the lens. And there is, there is a law about focusing which Abe came up with many, many years ago, in about 1880. And what Abe said was that with a microscope, you can't see anything smaller than the wavelength of light. And that's a real nuisance, because if you're a biologist looking at cells, the wavelength of light is just when the cell starts to get interesting. You can't see inside the cell without very, very special techniques. So that's a nuisance. And the reason you can't is that light actually has two characteristics. So if you have a surface and there's an atom emitting some light, then around that atom, the field has every possible detail that you could wish to examine the atom with down to the level of the atom. But only part of it escapes from the surface. Only that part which has the structure on the scale of the wavelength of light. And that's called the far field because it goes far. And there's another field called the near field, which decays exponentially away from the surface, and that has all these lovely details about the internals of the cells and so on. But we can't get at it with an ordinary microscope. But it turns out that Veselago's lens can. Not only can it focus the far field, it has a special way of grabbing the near field and bringing that to a focus too. So how does it work? And this is why I was scrabbling about my experiment. So you can think of Veselago's lens in two ways. One was the way Veselago thought of it, which was applying the laws of the refractive index. But these only apply to the far field. And that shows that the lens is perfect as far as the far field is concerned, but its resolution isn't perfect. Now, you can use another way of creating this lens, and that uses the transformation optics technique. So I'm going to start with some flat space, okay? Here's space. I haven't done anything to it. It's flat. But I'm going to make a Veselago lens out of it. So I'm going to squash space, and as you squash space, just as you squash anything, squash air, it becomes more refracting. So you squash space, it makes it more refracting. Squash space, and then you really, really squash it, and it goes infinitely refracting. Now, what does the function 1 upon x do when you go through 0? It goes up to infinity, plus infinity, and then on the other side comes down to minus infinity. And that's exactly what the refractive index does. So I'm going to shove really hard, it goes to infinity, whoa, minus infinity. So I've now made a piece of material which is negatively refracting because I've squashed it a bit more, okay. And then it comes not to minus infinity, but minus some reasonable number. And there you have a piece of negative refractive index. But you've done something really queer. What have you done to space? So this is 3 layers. So space, now instead of having 1 manifold, it has 3 manifolds. So as far as light is concerned, if it passes an object here, sees it, goes to the edge of the lens, goes through the lens, you think it's going that way, the light thinks it's going backwards, and it sees the object again and recreates it inside the lens perfectly. Because transformation optics obeys Maxwell's equations exactly, and Maxwell's equations are exact. And then it continues, it comes back, and it sees the object a third time. So that is the way to explain, if you accept the logic of transformation optics, how this lens can be perfect. I published that paper in the year 2000 after 6 months of vicious argument with referees who I could describe in a moderate language if pressed after the talk. But it did get published, and I arrogantly called it the perfect lens. And it caused quite a consternation because people really believed that Abbe's law was not just a law for ordinary lenses, they thought it was an absolute law of physics. Abbe had his law carved on his gravestone. I'm not so mean as to pay somebody to chisel it off, but it's still there. And that paper caused quite a storm. It's not a lot of citations in terms of biological paper, but in terms of physics, it's a lot. It had 16,000 citations last time I looked. I did say earlier on, how am I doing for time, by the way? 5 minutes, okay. Bit of transformation lecture here. I'm going to squash my lecture because I'm not even on to part 2 yet. Never mind. I'll go faster. But I do want to tell you about this, because I had said if nobody can make what you're talking about as a theorist, then it's going to, curiosity. But you can make this. And to explain how you do it, I want to say a little bit more about what light is. So I had explained, sort of, that light consists of an electric and a magnetic field. It's usually emitted by an atom from an electrical transition. So it starts off life as an electric field. And then it exerts a sort of dance, because the electric field is changing in time. That creates a magnetic field, and then the magnetic field creates an electric field. So light is a dance, but continually changing between electricity and magnetism. And the step of the dance, the length over which this change happens, is the wavelength. And the beat of the dance is the time period of the light. Now, having said that, if you only concerned with very, very small objects, which are much smaller than the wave of light, and an atom emits an electric field, and you don't give it the space to change into a magnetic field, you don't damn well care about the don't care about the magnetic field, because it isn't there. And therefore, the only one of the two requirements you need to satisfy of epsilon equals -1 and mu equals -1, because the magnetic field is not there, epsilon equals -1 will do, providing you don't go too far and look too far away from your object. And that was realized by my friend Jiang Zhang when he was in Berkeley. He's now VC, University of Hong Kong. And he had an object here which was much smaller than the length of light, 15 nanometer grating. Here's his lens, and it turns out that silver has a negative epsilon if you choose the frequency light. So here's some silver. Imagine making a lens out of silver. Anyway, this is what you can do. And here's a spacer, so that's... And then the object is written in terms of photoresist. You can't see it, of course, because it's less than the wavelength of light. And in comes illumination. And then you strip off the photoresist and you look at it in an atomic force microscope, and you can see that you can resolve the grating, a 60 nanometer grating, which is a sixth of the wavelength of light used. Now, a little more impressive is actually something you can read, which is this word nano written with a 14 nanometer line width. And if you don't have the silver in place, it's a bit blurred. And then you take a second image where you have the Vestager lens in place. It's like popping a specs on. So here's a scan through them, and you can see that the resolution is increased again by a factor of 6. It's not perfect, because silver has losses and things, but it shows you can do much better than Abe. Now, I'm going to skip through this very quickly, so instead of reading through all this stuff, I'm just going to say what you can do. So microscopy, there's something called structured illumination. So a microscope has two ends, and there's light on both of them. So there's the illuminating side that you don't normally think about, and then the side with the lenses where you sort of focus the image. But if you can structure the light coming in and have some sort of pattern with a very fine pattern on it, you can actually use, exploiting both ends of the microscope with structure, you can actually see very tiny things. But how do you make that very, very fine structure to illuminate it? You do it with this hyperbolic metamaterial that Xiaowei Liu at UCSD has designed. And here are the results of what he sees. This is the point spread function, which a scale of this is 0.1 of a micron, much less than the wavelength of light. And here are some biological specimens, and you can see what a mess an ordinary microscope makes of it, and Xiaowei's microscope is doing much better with very dramatic sub-wavelength resolution. What else can we do? Okay, you can make very, very thin lenses, and Capasso, Federico Capasso in Harvard, uses this concept. You don't have to have a lens which is lenticular in shape. You can replace the fat middle bit with a thin middle bit which has a bigger refractive index. So you can either grade the thickness Or you can have a constant thickness and grade the refractive index. And if you have a graded refractive index and you have a very strongly refracting metamaterial, you can make a lens which is very, very thin. And there's been quite a lot of progress in these very, very thin lenses. They don't have perfect resolution, but they do have this property of being very thin, much, much less than the wavelength. And here is a more impressive example of that, of a lens made for 3D imaging, made in silicon. It looks very pretty, doesn't it? So that's one imaging application of transformation of metamaterials. You can help with global warming. Jiawei Li, also University of Hong Kong, has invented this plastic sheet here. And he exploits the fact that heat usually comes in the form of long wavelength radiation when it's around you, heating you. And we give off infrared radiation, but it arrives as sunlight with quite short wavelength radiation. And you can have a sheet whose properties depend on the wavelength, so that this particular sheet reflects all the sunlight, or nearly all of it, but at the same time, if it's hot, it will also radiate the infrared as well. And even in bright sunlight, it has a radiative cooling of 93 watts per square meter. It's quite useful. These are reconfigurable metamaterials. You can make a satellite dish out of these, which are flat and has no moving parts, the parts of which you tune by altering in real time the properties of metamaterial. And these have been exploited in various communications with satellites. Oops, sorry. What else? Yes, you can also exploit these technologies in magnetic resonance imaging. Here's my colleague Richard Sims. And the thing about magnetic resonance imaging is that the signal comes as it says, an exquisitely small but sensitive magnetic field. And it's a very beautiful thing, because usually in imaging you're confronted with noise. And you are in the body. The body is an extremely noisy environment, but its noise is all electrical. There's almost zero magnetic noise in the body, except for these little MRI signals. So if you could keep the signal as a magnetic signal, you could have quite a low noise signal. And the time you spend in these horrible machines clanking away is determined by the noise background. And that's what Richard's trying to improve. Okay, I did mention that light, not only light, but also sound waves. So here is my friend Ping Sheng, and what he has here is an acoustic resonator. It consists of an elastic sheet with a little weight in the middle, and it wobbles. It's a resonator, like all those other things I showed you. And if you put them together, you can make extraordinary things out of it. This is a company based in Bristol and Sussex, which makes hospital screens, which are just an array of these resonators. They sell them to hospitals, and you put these screens, they're very cheap, put them around a bed, and if somebody's very ill there and can't tolerate loud noises, they will absorb the noise, and you can have a quiet, cloaked environment if you want. Okay, just finally, these are auxetic materials. This is mechanical metamaterial. Most materials, if you squeeze them like that, they go out in this direction. Auxetic materials, which you can design using structures, if you squeeze them this way, they go in the other way as well. You've all seen one of these. Have you ever wondered how a cork gets into a wine bottle? It's auxetic. If you push it, it goes in. So, and then it expands when you stop pushing it. So you've all seen a metamaterial. Okay. I'll skip over the future. You could ask me about it if you want. So, and you can read the summary. I apologize, Andrew, I'm over time. So thank you for your attention.
Thank you very much, Sir John. That was a terrific talk, and you took us through all sorts of areas of physics and science, which are both fundamental and applied. I think we're going to sit down here and have questions from the audience. Please take a seat.
Thank you. Yeah, thanks.
And before I open up the floor to questions, maybe I can make a few remarks that one can draw from some themes from the lecture. One is that the distance in time between the initial idea of negative refractive index and the first sort of practical devices was 30, 40 years, I think. Mm-hmm. So this illustrates, I think, how sometimes ideas just appear before their time. And also, as you said, that you actually have to do something useful with an idea, otherwise you're never going to become famous. Second thing is that the whole development of metamaterials has come about because of the way that you and others really understood the equations that describe the phenomenon of electromagnetism in materials. And that's a really impressive example of how a theoretician can have an impact in the field. And finally, I think it illustrates how this arc from very basic blue skies research eventually takes us on to very, very useful applications in many different areas. So maybe I can just start the questions by asking you, when you first started to write down that 1999 paper, did you have any inkling that all these possible applications could result?
No, I didn't. And that is another lesson that you may draw from this story, in that if there's a really good idea, it may start with one or two people, but its importance is demonstrated and made by many, many people. I mean, you saw those publications. I didn't write 4,800 papers last year. No way. I may have wrote 2 or 3, but not that number. And it's other people being drawn into the circle and bringing their own ideas to the party, many of which most of which I would not have dreamt of myself, particularly in the applied line and the acoustics line, which is not my field, that have really made it such a rich and rewarding place to be with your research.
Yes. All right. I'd like to invite questions from the audience. Just put your hand up and then wait for the microphone to come. There's one here. Gentleman with the black shirt.
Thank you. This was a very exciting lecture. My question is sort of about a statement you made near the beginning about how metamaterials exploit this size gap between the atoms and the wavelengths of light. And I'm wondering if there's kind of a rich detail within that, if certain metamaterials kind of have interesting properties closer to the size of the atom or closer to the wavelength of light.
Certainly closer to the wavelength of light. What happens there is that the subject of metamaterials morphs into another subject, which is photonic crystals, which is what brought me into the subject in the first place. There's a guy called Blavatnik who wrote an article, I think it was in the mid-'80s actually, in which he reminded or instructed, if you like, the optical community that there was something happening with semiconductor physics. So in semiconductors, you're dealing with electrons, which are waves, just like light, and they move in a structure of atoms. And they're diffracted by the atoms, and that diffraction creates a band gap. And if you fill all the states below the band gap, then you make an insulator, which is a semiconductor. That's the basis of a whole industry, a very important concept. But because light is a wave, you can also make a periodic structure, Blavatnik told us, which can create a band gap within which there is no light. It's not just black, there's just no light at all. So if you were able to be a sort of a little microscopic animal with a microscopic match, and you tried to strike it inside one of these holes, it wouldn't light because the light has nowhere to go. And the optics community found that really, really weird. And with semiconductor physics, they say, "You find that weird?" I said, "No, it's not weird." But it excited people a lot. John Maddox, who was editor of Nature, went bananas of it, and he said, "It's the only interesting thing in optics that I've heard of in my lifetime," which is nonsense, of course. But it did create a lot of excitement, and indeed, there are a lot of practical applications of photonic crystals, but they're different from metamaterials, because whereas metamaterials work on this sort of resonant picture that you get from an atom, photonic crystals work on an entirely larger wavelength scale. They're very clever things, but they're very, very difficult to design because you can't work with these parameters epsilon mu, which a metamaterial can. So all the technology of design which you have in optical engineering based on ordinary materials, you can say, okay, this is an extraordinary material, but can I use all my technology? But you can't do that with photonic crystals. Too clever by half.
More questions? So I think your hand was a nanosecond up faster than yours, sir.
Yeah, so my question is around these reconfigurable metamaterials you're talking about, because like one of the things which seems very exciting to me is optical signal processing with metamaterials, and I've seen people do crazy things like approximate a neural network with metamaterials, and like, is it then possible that we could be having software in metamaterials?
Okay, a very rich question, might I say. I'll try to limit my answer to more interesting things. What we're working on at the moment, and what my third section was about, is what we're going to do, what next? What did Pendry do next? And what we're doing next is looking at reconfigurable metamaterials, not just things that you can throw a switch and they change rather slowly. We're trying to change them on a time scale which is as fast or faster than the beat of light. And if you can do that, there's all sorts of amazing things you can do. You've mentioned one of them, computing or somehow signal processing. But there are other things too. So you can make, suppose you take, we've just been talking about gratings, yes, diffraction of light. So suppose you take a grating like this, and the light has a different speed according to the refractive index, a different speed. And then you make that move. You don't move a material, just move the pattern. It's like a wave on the ocean. The wave on the ocean moves. You're not shoving vast quantities of water around. You're just making the water go up and down at different paces. Same with this wave I'm talking about. So you make it move. And then if there's a point where the velocity of light in that particular refractive index is the same as the velocity with which you're making the grating, then just think what's happened. On this side, the light, let's say, is going slower than the grating, and so the grating catches up. On the other side, the light is going faster than the grating, and you get a sort of singularity here. And any light that's there is funneled into this thing. And actually, if you look into the quantum mechanics of it, it looks like a black hole. I mentioned this analogy between Einstein's metric and the refractive index. And that's what happens in a black hole. You get something called a Schwarzschild singularity, where the metric goes wild and light is captured there. And so in this structure. Now, one of the reasons that Hawking, despite his incredible brilliance, didn't get a Nobel Prize is that people never saw his radiation, right? And they never will, because his radiation has to escape after this massive black hole. And it's so far redshifted that it's so weak you'll never see it. So what people are looking at are laboratory analogs. And there's a guy called Unruh who has postulated several, but this is one of them. So out of, a very rich question, out of metamaterials which are structured in time as well as space, so space-time metamaterials, you can actually make an analog of a black hole which will emit radiation in pairs, actually, qubits, if you like. So, yeah, we're thinking about it. We have some experiments on the way. They haven't quite got the black hole stage yet, but we have hopes that they can do all sorts of things, including signal processing. Sorry, long answer to a rich question.
Very good. I think there was a question down the front here.
Well, actually, my question was virtually
Ah.
what was the most exciting development that you virtually told me?
Is there something more exciting?
Well, one of the things we've done on the way. So, one thing we do is as I say, my experimental colleagues, is we have a material which you can switch from being reflecting to transmitting, and you do that by blasting it with a powerful laser, which changes the electronic structure, and suddenly the thing ceases to reflect and transmits. And it did this so quickly, we couldn't measure how quickly it was switching. Of course, we're really, really anxious to know how quickly is it fast enough for other things. And so we stole something from young slits. Does everybody know? Who knows about young slits? Do our school people know about? Have you heard of young slits? Yeah, I see a nod. Okay, some people do. Let me just explain what they are. So Thomas Young, who was a great 19th century polymath, he decoded all sorts. Well, anyway, I digress. He did an experiment in which light hit a black screen with two slits in it. And it was to demonstrate the wavelength nature of light. So when the light hits the slit, on the other side, the slit diffracts it out into a broad beam. And it does so at the other side. And where these beams overlap, because light's a wave, and it has a different phase at each place, it interferes constructively and destructively in a series of fringes. Now, the spacing of the slits describes the period of the fringes, so how far apart they are, but the shape of the slit, how narrow it is, describes how broad that beam is, and it describes how they drop off with distance from the center. Now, we made an analogy, and other people have done this before, but we exploited the analogy between slits in space and slits in time. So we can make two slits in space. We don't know how narrow they are, but when we interfere them and put them through a spectrometer, so slits in space make fringes in angle. Slits in time make fringes in frequency. So if you put in a single frequency, the slit in time spreads out the frequency into other frequencies, and that will tell you how narrow the slit is. So we saw fringes which are amazingly extended, so our experiment was doing far better than we thought it was. So we're making excellent progress. We can now switch light within 2 or 3 periods of the light.
Interesting. So a question here, and then a question that in the front here.
Thank you very much for that. My question is on, obviously you've got a kind of theoretical background, but a lot of what you've spoken about has practical applications. Kind of if you were looking back over your academic career, what are some of the things that you would have done differently now looking back to kind of enhance that translatability from ideation to, developing something that has real world impact, if that makes sense?
Yeah. It happens, you might think that you design a perfect career for yourself, or try to. Of course, what did the famous boxer say? Everybody has a plan until somebody smashes you in the face. I didn't have a particular plan. I knew the direction I wanted to go, And I was fortunate in that I made few enough mistakes that I was reasonably successful. I don't think I made any very bad mistakes. In retrospect, there are avenues I went down that I enjoyed enormously, but in terms of, winning Kyoto Prizes didn't go anywhere. For example, I spent a long time working on disordered systems and proved some results there that I thought were extremely beautiful, but nobody else happened to cite. Was that a mistake? I don't know. It depends whether you're singly minded, wanted to go for, I don't know, some application or whatever. There's part of me that does design things. There's another part of me which says, que sera, sera. It's like watching a garden. You plant a flower and you don't sort of say, oh, you're growing wrong, I'll put a stick in, I'll make you go here and make you go there. You watch it blossom, and it is far more interesting than trying to control something. And your career is a bit like something blossoming that if it's going seriously long, obviously you have to have a big thing. But if it's going okay, relax, enjoy.
And there's a lot of serendipity in science, isn't there?
Sure. Yes.
And there's probably still discoveries to be made in fields that are apparently scientifically mature, just like what this field was.
Yeah, that's right.
There was another question, I think, yes. So, gentleman with the yellow hoodie. I'm surprised there's no questions about invisibility cloaks yet.
Oh, thank goodness. I hear with invisibility.
So I've got a question. Do you think there's a possibility for synthesis between metamaterials and other developing areas in physics, like, say, quantum computing?
Possibly, yes. Certainly with learning models, people, for example, if people are building structures which you can teach, which you might, there are many models of these. I mean, we have in the audience David Sherrington, and David was one of the pioneers of structures which are models for memory. And you can devise a series of metamaterials, and a colleague of mine in Hong Kong at City University is building a series of structures which you can train to recognize a pattern, say a flower, and the structure, you shine the light on this, and then it go through his series of metamaterials, and at the end it will say, yeah, it's pointing at that's a flower, whatever. Very simple things, but you can imagine them developing into more sophisticated. Now, you did also mention quantum computing, and I mentioned Hawking radiation. Now, the thing about Hawking radiation is that when you create the Hawking light, it creates two photons, and that's the qubit that is one of the elements that people use for quantum computing. So you might imagine some of these moving metamaterials being used to make the input to a quantum calculation. But that's a speculation, and it's so far in the future. It might blossom, maybe 20 years, I don't know.
There's a question, the gentleman with the blue tie and the white shirt.
My question was just on the Veselagos lens, and I was just interested on how the matter is folded rather than just compressed, as you said with the piece of paper.
Oh, this guy here. Yeah. Okay, it's a little more complicated than I described, needless to say. But yeah, I mean, if you squash space, then you take some air and you compress it, and eventually it becomes a liquid. And air isn't very refracting. It's got a refractive index of, I don't know, 1 part in 100 or something like that. And if it's a liquid, it will have a refractive index about the same as water. So you can change the refractive index by compressing something. And if you believe well, you don't have to believe me, you have to believe Einstein, that space can be compressed, then this analogy of making something have a bigger refractive index by compressing is a good one. The step which Einstein didn't take, because he was busy perhaps in more profound matters, is to realize that you can go beyond infinite compression and just go to that situation there where you overcompressed and made a negative thing. Whether that's helpful to you or not depends on how much you believe in mathematical analogies. Okay. If you don't like it, you can go to the mathematics, and that will tell you what I say is true. But I was trying to paint follow my hero Faraday and say it to you in words rather than formally. I hope it worked.
Is it possible to make a Veselago lens that can magnify by bending the light in the metamaterial?
Ah, yes, of course. That's one thing we've done with transformation optics. If you distort the lens, you can actually make a magnifying glass, a perfect magnifying glass. So something that we published as one of these things that never realized in practice is how do you make a parasol which is smaller than the wavelength of light. So you want to have a small object that casts a shadow that's much bigger than itself. That sounds really crazy, yeah? Okay, so I take a small object, which is much smaller than the wavelength of light, and I paint it really black. So anything it touches, it's gone, it's absorbed. And then I surround it with a curved negatively refracting material made in a certain way, and so on and so forth. And it magnifies that object. So have you seen these sort of pretty balls that have some object inside that appears to almost fill the ball, made of glass? So some glass will magnify an object inside it by the refractive index, okay? But if the negative refractive... So let me start with something even more simple. So if you have a swimming pool surface and you fill it with negative refractive material, and you put an object inside that swimming pool, then the light from the edge of it will come up like that, and the object will appear to float above the surface of the swimming pool. So when you have a negative refractive material, objects inside it appear as though they're outside it. So let me go back to this shadow that I'm making. I've got my block object. I surround it with negative refractive material, carefully constructed, and then you will appear to see this black object. It's really, in theory, you can make it as big as you want, okay. And then if you shine light on this, you find behind it a huge shadow emitting, but it's much smaller than the wavelength of the light. I can see you don't believe me. I had a student who wrote a PhD on it.
All right, there's still time for a question on the invisibility cloak.
Hi, I would just like to say that it was a very good talk. My question wasn't really about the invisibility cloak, but something similar. You've talked a lot about metamaterials in the wavelengths of radar and infrared, but is there any way to tune the metamaterial such that it operates over a wider range of frequencies, such as visible, ultraviolet? So is there any challenges in doing that?
Yes. I mean, one qualification is that this Vesco-Largo lens, the rules of physics dictate that it operates over a very narrow band of frequencies. Otherwise, you run into logical paradoxes. You can imagine somebody traveling around this curve and seeing himself, for example. And unless you have very, very strong dispersion, then that breaks laws of logic, let alone anything else. But most structures made out of metamaterials, such as cloaks people have built at radar frequencies, they are relatively broadband. So they could cover, like, I don't know, 30 or 40% of the operating frequency. And there is no stealth that's infinitely broadband or whatever. As to range of operation, people, it's very cheap to make things for radar, and that's where a lot of the early work came. But now people have technologies that can make structures really on the scale of visible light, and there are a lot of people who are making lenses. I showed that Capasso lens, which was for infrared, but that other silicon lens I showed was working in the visible range of frequencies, and it was a metamaterial lens. It's quite expensive, of course, because you've got to etch silicon, but nevertheless, it's within technologically doable things, and some of them they've engineered to be broadband as well. Yeah.
Wait.
What happens when a charged particle goes through these materials? I can see a conflict between Cherenkov radiation on the one hand and accelerating phenomenologies on the other. It sounds a rather interesting laboratory.
Yes. Okay. Well, I can answer that in the following way, that we know what happens when, could I ask, are you in electron microscope? Do you work with electron microscopes? Do you work with electron microscopes? No, okay. Well, people who do know what happens if you send an electron into a metal, okay? And a metal has not a negative refractive index, but it has a negative epsilon, and the electron has a negative charge. And what happens when an electron goes into a metal is that it radiates inside the metal oscillations of the electrons, which are called plasmons. So imagine we think of the electrons in a metal as a liquid. We call them the electron liquid. And like every liquid, it will wobble. It can wobble like a jelly, and that jelly is a plasmon. So an electron disturbs this electron jelly, and it shakes. And that's where all the electron energy goes. Now, a negative index material is a little more complicated, because it has a plasmon, an electrical plasmon, but it also has a magnetic plasmon. But it's mainly the electron, it's mainly the electron plasmon that the electron would see. So you're probing much more deeper into this subject and asking about all sorts of fancy dispersion relationships. But basically, it makes the stuff wobble. Yeah.
I think before we get any deeper into the subject, we probably should draw this discussion to a close. We've worked you very hard. Congratulations again on the Kyoto Prize, and thank you so much for your lecture.